Today, I'm not going to be talking about Kubernetes. I'm going to be talking about machine learning design patterns that are useful for data engineers. Okay? So what exactly are design patterns? These are things that are pretty familiar to software engineers, right? These are formalized best practices for problems that happen over and over again. And now that we've been doing machine learning in production for several years now, we have built as a community a lot of experience in terms of what actually works in terms of machine learning. And we thought that this was a good time to basically start recording some of these best practices. Because if you're new to the field, you don't know that this is the right, these are things that people have tried before, and here are the trade-offs, and this is why you use what you're using, the things that some of the names might appear in the APIs, but you might not realize the reason why you're doing things in a certain way. So knowing the design patterns, having names for them, really helps you become a much better machine learning engineer, because much better data engineer. So what we did was that we captured 30 of these design patterns in this book. And what I'm going to be doing in this talk is that I'm going to be talking about 3 of them: transform, stateless serving function, and continuous evaluation. Now, in addition to the book, there are example implementations of all of these design patterns in this GitHub repository. And so I really encourage you to go look at the code to give you an idea that this is how people actually implement this in real life. So what I'll be talking about here are primarily about the concepts, but these are all very real and implemented and part of many production ML projects and things that are used by a lot of teams. So let's start off talking about the transform design pattern. This is design pattern number 21 in the book, 21 out of 30. Okay? And let's kind of frame why we need this in the first place. So imagine that we have a machine learning model, and it's going to predict the length of time that somebody is going to keep a rented bicycle. So they rent the bicycle at some particular station, let's say King's Cross station in London, and they rent it on a specific date. And we want to be able to predict that if they rent this bicycle on April 22nd, 2021, right, and they rent it at King's Cross, how long are they likely to keep this bicycle around? This is going to be important because we want to stock bicycles. We want to know when to do maintenance on the bicycles, et cetera, et cetera. So in order to do that, we train an ML model. And the ML model basically takes a station name, it uses it as an input, and when we give it April 22nd, 2021, it pulls out Thursday, and it pulls out the hour of the day, pulls out, let's say it pulls out 18Z, right? In London. That's the time that it pulls out. And it goes ahead and trains an ML model to predict the duration. Okay? So that's basically what we have. We have 2 inputs, station name and start date. We have 3 features that we have into the ML model, right? We've pulled out the day of the week and the hour of the day from the inputs, and we use it to train an ML model. So this is great. We trained the ML model. The model now basically works, and it's basically, we take that model, we deploy it, and now we want to run this model in production. What inputs does the model want? Does the model take the station name and the start date, or does the model require station name, day of the week, and hour of the day? It's pretty clear the model was trained on 3 inputs. So it's going to need 3 things, which means that this poor client here has to somehow know what the model developer did in pre-processing and feature creation in order to call this model. And this is a huge problem. This is what leads to training serving skew, because the model developer might have done everything in Python, and now we have to basically go find the equivalent thing in Java or JavaScript or whatever it is that we're going to be doing on the prediction system side to pull out the day of the week and the hour of the day, right? So the problem here is we've trained a model with the duration, we've extracted out the day of the week and the hour of the day from the data, and we've trained the model with 3 inputs, which means that whenever somebody calls this model, they have to know, okay, King's Cross is a station name, but they have to know that in the training system, Thursday was represented as 3, right, in quotes, as a string. How do I know that? How do I get a library that gives me that? And that is a huge, huge problem, right? And it's a leading cause of training surfing skew. What we really want to be able to do is what we can do and say, this is BigQuery ML that I'm showing you. It's a SQL way of doing ML models. And the idea is that even though you pulled out the duration, which is the label, the start station name, and the start date, those are the inputs, you now basically say that the model needs to transform. And what it needs to do is to take the start date and extract out the day of the week and the hour of the day, and then train the model with the duration as the label and 3 inputs. And now that the model is trained in this way, we've kind of kept the inputs and the features separate. And that means that when we go ahead and do a prediction, it's as easy as saying King's Cross and the current timestamp. And the model, internal to the model, it has captured all the pre-processing and feature engineering that has to be done on the input data to get to the model. So as you can see, this becomes a lot simpler from a productionization standpoint if we take the transforms and we put them into the model graph. Now, what I showed you was BigQuery ML and SQL, but you can do the same thing in TensorFlow and Keras. So the basic idea is pre-processing that you're doing, put those transformations in Lambda layers and Keras. Because if you do it in your Lambda layer and Keras, now when you do a model.save, the Lambda layer also gets saved with the model, which now means that your model works on the raw input data. And therefore, it becomes much easier to productionize. So in this case, we're just showing you an example of, let's say that we want to take latitude values and basically do x plus 78 divided by 8. Well, normally you might do it in pandas and then save out the transformed data and train your model on the transformed data. And what I'm saying is like, that's a bad idea, because now you have to basically remember in every production system that you need to add 78 to latitude and divide by 8. I mean, who's going to remember that? How are you going to keep that up to date, etc.? So much simpler if you have these kind of simple scaling, formatting, clipping, all of these kinds of things. Throw them into a Lambda layer in Keras, make it part of your model. So this way, now your model, right? You have 3 things. You have inputs, which is the raw data, with the features that you've created, and you basically go from inputs to features using these transformation layers. And this is the way, when you keep them separate, it basically becomes productionization become easier. So the basic transform pattern is that the model graph includes the transformations that you do to go from the inputs to the actual data that you use in your ML model to train the ML model. The model still uses 3 features. But the key thing is that the transforms are layers in your model graph. And because they're layers in your model graph, it becomes so much easier to productionize. Now, is this the only way to do it? Absolutely not. There are lots of trade-offs here. And in the book, we talk about 2 other patterns. We talk about TensorFlow transform, which is a way of basically making things more efficient so that you're not doing it in Lambda layers. We talk about feature store, which is another way of making things more efficient so that you pre-compute these things beforehand. But transform is the simplest pattern that allows you to limit training surfing skew. So it's worth knowing, and it's worth implementing in a lot of your projects. The next pattern that I want to talk about today is a stateless serving function pattern. Okay? So why does this come about, right? Imagine that you've trained an ML model, right? You've trained a model that you basically pass in some text, and it basically gives you a classification, some kind of logics. Maybe it's sentiment, maybe it's topic modeling, it's something. Now, in order to basically call this method in, like when you want to predict with it, you would just call model.predict and pass in a tensor corresponding to the sentences for which you want the sentiment or topics or whatever. Now, this is problematic because what? You need the model in your prediction system. So you have to load and retain this entire model into memory. And that's pretty wasteful because a model contains things like the epochs, contains dropout nodes. It has a whole bunch of state that you don't really need for predictions. Secondly, the model typically is not thread safe. So you're going to have latency limits. You cannot basically just call this all the time. You cannot thread it, right? You cannot do things in parallel. And also, just as with the transform that I just talked about, you will often need to support a different input than what was used in training. So when you're doing training, maybe you just train it on a single sentence at a time, but in your prediction system, you want to take a paragraph and you want to split it into sentences and then call the predict on all of those sentences. And that's what your API needs to be. Your API that you're using for prediction may not be the API that you use for training. And so, relying on model.predict is problematic. So what do we do? Well, one way to do this is to export the model. So you basically take your model and you basically say, okay, I've written this model out, and now I can just load the model. And when I load the model, I just retain what are called signatures in the model, right? And the signature basically is the thing that you call, and the signature matches the input layer of the Keras model. So now you basically get a function, and you can basically call that function, passing in the whatever data is needed by that function. And now this function is something that you implement to invoke the model. So this is great, right? So prediction signature, you have this idea of a function that is separate from, right, the input layer, but the prediction signature matches the input layer. Okay, but if the prediction signature and the input layer are the same, then you still have abstraction problems because, hey, remember, you're still loading the model. So that all of those problems exist still now, and it only works in Python, right? So you still have your abstraction problems. So what's the solution here? The solution here is to use a stateless serving function. The idea is that you take this model and its serving function, you wrap it up in a web serving infrastructure, that is capable of accelerating and running on like accelerated hardware like GPUs or TPUs. And you put that into a managed platform, a managed cloud provider like Cloud AI Platform or SageMaker or one of those like services. And now basically this entire thing becomes a web microservice. So you still have your model, but you've wrapped up your model into a framework that's capable of being accelerated in another framework that gives you managed services that automatically scale up and down, right? Depending on the amount of traffic, they do load balancing and all of those things that you would expect of a web microservice. So now, as far as a client is concerned, they just need to give you a JSON and you will give back them a JSON. It's now a REST API. And they can forget that they're calling a machine learning model with tensors and all of that stuff. They're just sending you a JSON request and getting back a JSON response. So why does this work? It works because this ability to scale web endpoints, and remember, this is what TensorFlow serving does. It gives you a web endpoint. Auto-scaling a web endpoint is a well-understood engineering problem, right? All of your cloud providers know how to do that. No big deal. It's fully managed. The cloud platforms abstract away the managing and installation of like TensorFlow and all of that stuff. They basically give you, if you use AI platform, you use SageMaker, you use Azure, right? You basically get this, all the installation stuff out of the way. You don't have to worry about it. The prediction system is already done. Now, because you're sending back and forth REST APIs, it's language neutral, right? You can do this from Python, you can do this from Java. You can even do this from PHP if you want, right? Everybody knows how to speak HTTP. And because these are web applications, you have a really powerful monitoring system, right? So all of your ML ops become a lot easier because ML ops is now just DevOps. You're monitoring and throttling your tools. No, and your SREs know how to do it. Your IT admins know how to do it. Your DevOps people know how to do it. So this is why you basically have these 3 layers of the onion, and it's super useful to be able to do that. Okay. Now, how does it matter to us as data engineers? Well, remember I started out by saying you need abstraction, and the serving API, the default one, basically gives you the same inputs as the Keras model, but you don't have to live with that. You can change the input signature. So what you can do, for example, and I'm showing you a very simple example. Let's say that every time somebody gives you a file name, they also give you a sequence number. And when you return the result for that file, right, you also need to provide the sequence number that they gave you with the file. You need a pass-through. Well, the sequence number was not an input to the Keras model, so it will not normally be present, but it's very easy to add it. This is what you do. You write a function, you add a TensorFlow, you say that this is a TensorFlow function, you get the original serving default, you make the original call, you get your result, but this result is a Python dictionary. So go ahead and add in, right? Here are the file names you gave me, here's a sequence number you gave me, and there is your result. So now you basically get back a JSON that has what the model would have normally provided as output, but also some input pass-throughs. So now when you export the model, when you save the model, you can save it with 2 signatures, one with the original serving default and another one with an input pass-through. And then when somebody calls your model, they can choose whether they just want the bare bones functionality or they want this additional functionality. And obviously, as you can see, now it's just basically based on the JSON request, and you can do anything that you want in here. You can call your backend database, you can enrich the data, you can do all kinds of amazing things in this prediction signature, because this prediction signature is separate from your ML model. So this gives you a lot of abstraction and a lot of new capabilities that you can add to your ML model. So that's why you have this concept of a serving function and this idea of having it be stateless so that it auto-scales. The third pattern that I want to talk about is that of continuous model evaluation. If as a data engineer, one of the things that we often want to put in place is a way to detect things like data drift and concept drift, right? So continuous evaluation is well after the normal parts of your ML lifecycle, where you're basically exploring data, building an ML model, and you're deploying the ML model. At some point, you will want to start monitoring a model that you put into production to see if it is still performing as you would like it to perform. Okay, why? Because models become stale over time, right? For example, right, when the credit card started to have chip-in-pin technology, right, it became really hard to fake a credit card in the physical world. So many more fraudulent transactions start to move online, which means that any fraud detection model that you trained is going to be very, very, very sensitive to the fraction of chip and pin transactions in that data set. So over time, this probability distribution is going to keep shifting, and you have to keep retraining the model every time the performance drops. Okay. Another reason for concept drift is that, like, if you have a word model, the meanings of words changes over time. Well, when people talked about trolls, right, they were talking about dolls before, but now they're talking about annoying people online. When people talked about cells, they were talking about prison, but now they're talking about mobile phones. We talked about cloud, they were talking about meteorology, and now we're talking about data centers, right? So these words acquire new meanings. So you have to retrain models that are reliant on language. Okay, so the other thing that can happen is that the probability distribution of data itself can change over time, and that basically causes models to become stale. So how do you do this? You need a way to compare a model prediction with ground truth after the model has been deployed. So the way we do this, right, is how do we do this? Well, because we have a model already deployed, it is receiving new data all the time. That's a key thing to realize. It's receiving new data all the time, and it's making predictions on that data. And in many cases, we can go find the ground truth. The ground truth might be delayed. So imagine that you are basically training an ML model to predict whether somebody's going to abandon a shopping cart. Well, 24 hours from now, you know if the shopping cart was abandoned or not. It's just delayed, right? Other ways is you might have to basically save your part of your input data, send it to human labelers, and have them label that input data, and that way you get your ground truth. So the idea is that you save the predictions, not all your predictions, because that will slow things down, but a fraction of your predictions, usually like 0.5% or 0.1%, 1 in 1,000 predictions, so that you can basically compare it with the ground truth. And so what you will then get is a table that looks like this. Here's the model, here's the version number. At this time, you basically go ahead and you had your, this is the text that you passed as input. This was the output that it provided, the probability, the output thing that, now the actual, then you have to fill in the actual ground truth when you do have it, right? And you might have it through human labeling. You might have it because later on, right, you basically have a better way of finding what that actual answer is. And now you go through your sampled predictions, and now you have a new data set. And what you do is that you compare this data set over time. You say, okay, let me go ahead and find the evaluations for more than a month ago, more than a week ago, etc. And you start comparing it. And what you will start to see is that as time goes on, performance will start to dip, and you might set a threshold and you say every time the performance goes below a threshold, go ahead and retrain. We can, once we do this, it also allows us to compare performance across model versions, right? We have a new model, we can basically take the same input and split it, and we have this new model running in the shadows. So the first V1 is what is being used in production. We have a shadow model, which is V2, that is all of the traffic is being sent to it. And we're saving the results of both V1 and V2, a sample of them, into our evaluation database. And then once we get the ground truth, we compare against that ground truth. And then we basically see when do we switch over from V1 to V2, right? So how do you get that? Oftentimes, it's just a matter of time, right? A month later, you know which transactions are fraudulent, right? When somebody basically comes and complains about it to you. Now, a few days later, you know which shopping carts were abandoned, okay? Other times, you may have to actually do human labeling, okay? Or you might, if it's a medical situation, you might know if this patient had to be readmitted, etc. So you basically use that. You look at how the performance changes over time, you retrain, and what you basically get is a performance curve that looks sort of like this. Okay, and the idea is that if you can do this much more often, now you basically get the ability to maintain a much higher performance, right? So the idea is you start setting this up so that as you get new data, you take that new data with the ground truth, you throw it into your training data set, you retrain automatically, and you set this up as an automated process. Okay, so if you don't do this, what else are you doing? Well, what you might be doing is that you might be doing things in an offline environment. So you train a model on some data, you basically put it into production. 6 months later, you take that old model, you now have new data that you've collected over the last 6 months, you evaluate on that data, and if it's not good enough, you start doing the retraining. What we are doing with continuous evaluation is that by saving this sample of predictions and over time, we basically get the ability to continuously improve it. So with that, like I'll come to the end of my talk. We talked about 3 patterns here. Again, 3 of the 30 ones that we cover in the book. So there's the link to purchase the book. You can get a free trial to read the book online. That's the code for that trial, MLDP, Machine Learning Design Patterns 20, because the book came out in 2020. My co-authors, Sarah Robinson and Michael Munn, you see them on the slide here. Follow me or Sarah on Twitter. Michael has a life, so he's not on social media, but both Sarah and I are. So you can follow us on Twitter. You can read our blogs, and again, all of the code to illustrate how this all works is on GitHub. Thank you.
Michael has a life, so he's not on Twitter or social media. I love that, man. I love your presentation. That was great. Seeing you again present. You got a minute to answer some questions?
Absolutely, absolutely.
Awesome, awesome. So, of course, I asked you all the questions I could ever ask in the hour that we spent together, and I highly encourage everyone to get this book. Definitely, I got it. We've been talking about it in Slack. It is very cool. The question coming up, is there going to be a new edition of your book?
Is there going to be a new edition of the book? I mean, there over time, I'm pretty sure that we will identify newer design patterns, and some of these design patterns will become obsolete. And so I imagine that we might want to do a new edition of the book. We're not ready to think about it yet, right? Writing a book is a largely thankless job. It takes a lot of time away from doing the things that Google pays me to do. So yes, maybe. At this point, I've only identified one idea that I might want to include, which is about how to represent geospatial data. So maybe I might just do blogs instead. And once we have enough material in blogs and articles, we might consider basically doing a book. But I mean, and the other thing about doing a book is that you always have to drop things. I think 30 is about the limit. So we'll have to go back and take a hard-nosed look at the ones that stop being relevant over time. At this point, the book is only about 6 months old. It's all pretty relevant, so I don't see a need to change it immediately.
Yeah, and they're already asking for the new updated version. Oh man, it's ruthless out there, Lak. And I think it's funny.
Tough room.
Yeah, exactly. It's also very funny that you say that it takes you away from doing the stuff that Google pays you to do. So I can understand. Now, keeping with the book theme, what is that bird on the front cover?
This bird is called a sunbittern. It's kind of like a wild turkey from South America. And those, it has this, it's like a peacock. When it spreads its feathers, you basically get these huge eyes. So it makes the bird look like it is much larger than it is. So when it sees this predator, it basically spreads its wings, and then you get those red spots. They look like huge eyes. You should go look at a photograph online, right? It's amazing. And it basically looks like it's a scary thing. And no, I did not get to choose the bird. I just love the bird. I had not heard about the bird before. O'Reilly assigned the bird to our cover, right? We authors don't get to choose the animals on our covers.
All right, so people are getting pissed at me that I'm not asking any machine learning related questions here. Here we go. What are the cons of putting feature engineering as a layer instead of doing it outside?
Yeah, absolutely. And this is something that we get into quite a bit in the book, but let me kind of summarize. Number one, training a model is an iterative process, which means that if you train the model for 100 epochs, there's 100 epochs times that you're basically doing this pre-processing over and over again. So the more expensive your pre-processing is, the more computationally expensive your training process becomes. And the way to address that, that's what TF transform does. TensorFlow transform basically figures out a way to do this only once rather than all the time, but still have the stuff be part of the model graph. The con is now your architecture is a lot more complex. You now have to have TensorFlow transform. You need to have a Apache Beam. You need to have these artifacts in your model pipeline, right? Your setup becomes more complex. The nice thing with the transform pattern is that it's simple. The trade-off is you're going to be doing these computations many, many times. Your computations are cheap. Your time is more valuable than the computer time. And I strongly recommend that you let the computer work a little bit harder so that you don't have to be up at night answering pagers.
Incredible. I love the way that you put things, man. All right, you got to come back on the MLOps community meetup, because having you on here just inspired me. There's so many questions. There are a bunch left in Slack. We have probably time for one or two more, maybe, depending on how short-winded or long-winded the answer is. So if you're building a batch system, is it still advised to host the model as a separate web service?
If you're building batch systems, is it yeah, that's a great question, right? And again, there's an entire pattern called batch serving that we get into many of the trade-offs here. So I'll kind of summarize a little bit here. In some cases, you want it to be a separate service. In some cases, it is a good idea to load it internally, but when you load it internally, you have to be very careful to basically take into account things like state management and things like distribution of model state. So it is not, so there are times in which you will want to keep it as an API, and times in which you want to keep it as a shared model handle, and times when you want to load it as not a shared model handle. So all of these possibilities, there are instances in which they're the right approach, right? So it's not like you do one always, but there are certain classes of problems for which you want an API, certain classes of problems for which you want to load the model into the pipeline, certain class of models where you want a shared handle in an Apache Beam pipeline, and we talk about those.
Nice. All right, last one, and then we really got to go. So could you just, oh no, wait. Sorry. Is there any study that shows that overfitting decreases or increases as we do continuous model evaluation?
Is there a study that talks about overfitting and continuous model evaluation? Well, whether you do continuous model evaluation or not, right, you do need to train on a representative sample of data. And all we're saying with continuous evaluation is that the world is dynamic and the representative sample of data will change over time. So I don't know, you are not training exclusively on new data. If that's what you got out of it, I'm sorry, that's not what I'm talking about. You're continuing to train on a representative sample of data, and you're hoping that like over time, if the probability distribution of your features change, that you're dropping the older bits and you're replacing the older data with the newer data. So think of it as training on a moving window of data, but that moving window of data is still a representative sample. It's very important that it is representative.
Excellent. For any more questions, go read the book. I got an affiliate link that I can make $5 off if I'll share it with you. All right, Lak, man, this was awesome.
Absolutely, and yeah, all the royalties from the book go to Girls Who Code, by the way. So you're always nice. Also supporting a good cause.
Oh, you're making me feel bad with my affiliate link. All my affiliate link royalties go into my pocket.
No, that's fine. That's yeah.
I'm joking with you, but thank you, man. This was awesome as always. I really appreciate it.
You're welcome. I'm sorry, I cannot see Slack the comments, but if any of you have questions or anything, I'm available on Twitter. Just feel free to tweet it.